Okay, so let's talk about respiration in fish. So they have gills and it's in their pharynx. And so water actually needs to come in through the mouth. They need to close their mouth and then they need the water to run over their gills and out. And so when we look at this, we have when water is taken in, it is taken into the mouth. Okay, so we'll write mouth opens, water moves in. Mouth closes, and then the gill covering, which is called the operculum, it's a covering of the gill, opens, and water moves out over the gills. Okay. Now remember that the gills are thin. They're obviously moist because they're in direct connection with the water so that the oxygen can be dissolved in water. It's dissolved in water and it diffuses from a higher concentration to the lower concentration. But when we look at the respiration in fish, they actually have an interesting mechanism, and it is called the counter current mechanism. And this describes how they can efficiently extract oxygen from the water. So allows for like up to 80% of the dissolved oxygen to be extracted. Okay, so let's look at a diagram that shows this. This is, it doesn't really show the operculum, but here this is the gill and the gill arches. This is what shows the counter current exchange. So what is current? What is moving? So we have water flowing in one direction. So we have water. And we have blood flowing in the other direction. So this is counter current. If it was concurrent, then water and blood would flow in the same direction. Am I going to move myself? There we go. So water, so this is versus this. So what variable does this influence in terms of the rate of diffusion and that formula, that mathematical formula? This affects the delta P. So this influences delta P. Why? That is, remember, the concentration of oxygen. So if we look at an example of some numbers, so I have a cheat sheet here. Okay, so let's say that in the water, the concentration starts out at 150, it goes to 120, it goes to 90, 60, and I didn't draw my arrow long enough, and then 30. What is this? This is partial pressure of oxygen. That O2 is lowercase, and this is in millimeters of mercury. So that's the unit. Okay, so if these were running in the same direction, then what would happen would be that blood with low would be coming in, and it would have diffusion until there would be some kind of equilibrium, and then diffusion would stop. So here we have oxygen poor blood coming in here, and it's 20, and then it's 50, and then it's 80, and then it's 110. And so you see that it helps to maintain the differences. So all along, so even when my blood has a partial pressure of 140, I can still extract oxygen from that, even if, okay, what if it was going the other way? It might look something like this. Water starts out at 150. Let's say your blood starts out 20. And then it goes to, let's just skip some of these. Let's say it goes to 90, and then it goes to 80, and then let's say it goes to 60 and 60. Okay. So the differences in the partial pressures between the water and my blood are the same. So it would reach an equilibrium and diffusion would stop. So right there, diffusion would stop. And so I can't get any more oxygen out of it. But look at up here. I could get, even when the oxygen in the water was at 30 millimeters of mercury, I could still extract some. And so that is the idea of counter current exchange. It is used in engineering all the time, counter current exchange. Okay, so that is how it influences this variable. So if I increase this difference, right, it goes faster, but by having this counter flow, then it picks up more.